So in this video, we are going to understand the problem of calculating minimum spanning trees for graphs. I'll discuss two algorithms for computing minimum spanning trees of graph. But first, those algorithm are Prim's algorithm and Kruskal's algorithm. But first, let's talk about what is minimum spanning tree. What does that mean for a graph? What is the problem of minimum spanning tree? For example, I have a graph. Let's say, okay, fair enough. This graph, okay, and each of these edges have costs. Let's say 1, 2, 7, 9, 9. For variety's sake, 10 and 11. Now the question is, calculate a graph such that it is connected. By connected, it means that each and every point can be reached from each and every other point, and the sum of its edges are the minimum possible. That means that whatever the edges in that present in that graph, in that minimum spanning tree graph is, the sum of those edges is the minimum possible for all possible spanning trees, minimum or for all possible spanning trees. So for example, in this case, it would be something like, because I've chosen this graph in such a way that it can be represented 1, 2, this one, this one, this one, and this one, and then this one. So basically, only this 9 edge cost with number 9 is omitted, because by omitting this edge, all of the vertices are still connected with each other. And if I were to swap the 7 with something else, like for example 9 here, it will be only raising in cost. So why is it called minimum spanning tree? I should have mentioned it earlier, but the thing is that it is a tree, that is, there are no cycles. So each and every point is connected to each and every other point through one path only, and as there are no cycles, it is that is the definition of a tree. Okay, so what does it mean? How do we calculate a minimum spanning tree? So that's the question. So you understand the problem of minimum spanning tree, and I don't think it's very hard to believe that this can come useful in many aspects. I don't have examples in my mind, but let's focus on the algorithm, on how to calculate minimum spanning tree of a graph. So we are going to talk about two algorithms, Prim's algorithm and Kruskal's algorithm, and both of them are very intuitive, and both of them have a very nice running time, you know, and they can be very easily understood as well. So what Mr. Prim, whoever he is, came and told in his algorithm is, for example, you have a graph, any random graph, and what you do is, so in this case, it's a very highly cyclical, very connected and very highly connected graph. And so what you do in this Prim's algorithm is choose any arbitrary vertex, let's say vertex S, choose any arbitrary vertex S, and maintain a set of all of the edges in the minimum spanning tree. So in the start it will be a blank set, but as and when you progress, you keep inputting edges whichever you are trying to include in your minimum spanning tree. Now, how do we choose which edge to put into this minimum spanning tree? Well, you choose that edge by using this particular thinking, that whichever is minimum going out of our current spanning tree is the one we are going to include in our spanning tree. For example, let's do some example on this algorithm, right? And then I'll give you a pseudo code sort of definition. So for example, I have edge cost 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay. And I choose, let's say, vertex, this vertex here. We start here with our minimum spanning tree. So I include this in my set of vertices, and I initialize a set of edges which I will put to be blank. Now, what is the minimum edge going out of this particular spanning tree that we have till now? This one, 6, edge number 6, which is going here. So we'll input that in our minimum spanning tree, edge number 6. Now, and we add this edge number 6 to our edges. So now I have my vertices and edges which I'm going to maintain. My vertices contain the first vertex A, B, C, D, E, F, and G. So my vertices set will contain vertex A, and my edge set will contain this edge with thing 6. Now we have also input edge vertex G in this first iteration of the graph, and now yeah. So now looking at this, now in the next iteration, considering our vertices to be A and G, which is the minimum edge going out of this A and G. So it's going to be 12, 7, 5, 4, 1, 2, 3, because G connects all. So minimum of this is 1, right? So I am going to add vertex F into my F, and I'm going to add this 1. Now next, of AGF, which is the minimum, it's going to be this edge with 2. So I add this E, I'm going to add 2, and I think it's not very hard to see how this will keep on going till it gets to 3, 4, and 5. It's just how the graph is designed. E, D, C, B, E, D, C, B vertices. But after that, what after that? So I have A, G, F, E, D, C, B. So in fact, I have all of my vertices included. And this is how my minimum spanning tree looks for this particular example that I have taken. 1, 2, 3, 4, and 5. Okay. None of these edges outside are considered, right? So here's the pseudocode. Here's how it looks. Let's put it into words. So Prim's MST algorithm. I will initialize a set X. First step. Step number 1. I initialize a set X that will be equal to this S. This is just the first node. S is chosen randomly, right? Okay. Then I have second step T. This is an empty set, and T is the set which contains all of the edges which we have spanned so far, right? That's what T means. Now the first we are going to maintain an invariant, that is X will contain all of the edges, all of the vertices that we have spanned so far. So as you see, we built this V set one by one. Here I'm calling X V, the same thing. So here's the invariant for these two initialization steps. Invariant X is the set which contains vertices spanned so far. So here a bit of bookkeeping before we get into it. I am don't think it will be difficult for you to understand how I will represent graph. Graph will be represented as a set of vertices and edges. So I'm going to call V vertices. Here I call V, let me rename it to be X. But vertices V will be all vertices of a graph, and E will be all edges of a graph. All right. Okay. So now we get into the meat of it. While X is not equal to V. So as long as we are not inputting all of our vertices into X, that is X does not span the entire tree, we're going to keep going in this loop. And what will be the first step of a loop? Let an edge E be UV, that is edge E goes from U to V, or edge E connects U and V, where U lies in X and V lies outside X, right? So this is what we did here, when we went from vertices and we saw all of the vertices going out of our particular graph which we have made up till now. This is what this step means. We'll calculate all of the edges where first endpoint lies in X and second endpoint lies outside X. Now we're going to find out whichever is the minimum of these E. Find minimum of all these E's, right? And then we are going to make that our candidate for adding into our minimum spanning tree. So we'll add this edge E to T, and we're going to add vertex V to X. V here is whichever vertex whichever vertex gives the minimum E, right? So there will be one distinct edge which will have minimum weight, and it will connect U and V, where U is in the graph and V is outside the graph. So we'll include this V in our tree, and we'll keep on going on this until we have exhausted all of these vertices, and X will finally be equal to V, and at that point we will end.